And we're live. Hello, Verge.
Hi, Mark. How's it going?
Oh, just dandy.
Wonderful.
As my hand dissolves into your kitchen. Okay. So what are we doing today?
Oh, we got good stuff today.
All right. I'm Mark Corelli from Ryan High School in Denton, Texas.
And I'm Verge Cornelius from Lafayette High School in Oxford, Mississippi.
All right. Those of you that are not joining us for the first time, this will be new. Everyone else, old news. Point your phone at the QR code. Write down the bit.ly, pause it if you need to. That's our schedule for the next few weeks, how we're going to review for the coming test, which is on May 12th at 2 p.m. Eastern, same time as we're here now, right? It's actually,
That's right.
It was 4 weeks ago, 4 weeks from now, yesterday.
That's exactly right. Yeah, 4 weeks from today, you will be done with your AP Calculus exam.
It'll be a day away, and you will have forgotten everything you wrote on the test.
You'll be scrambling for another AP, probably.
Except for that one moment in the shower when you're like, oh. All right. So, how are we doing?
Very well, I must say.
Excellent. So,
yeah, we'll see what today brings because, we got good stuff today.
I don't want to plan on an accident, but I do like the fact that I'm getting tired of the picture, which is a good sign of our consistency. All right, so introduction to banter is over. We've got our warm-up coming up very soon. And today's title, there are a lot of words there, but it's really just
chain rule. chain rule. Yeah. In fact, I sang a little bit at the end of yesterday's lesson, chain of fools. And we would really love to play live music for you, but unfortunately the way the streaming works and copyright laws work and things like that, I can't play any sort of live music. So you're stuck with my voice.
Don't want you to come back tomorrow and just have a black screen, video no longer available.
Yeah.
So yeah, and for those of you that hung on to the very end, Little Richard did a cover in 2011, but Tom Convoy wrote it and gave it to Aretha Franklin, even though he'd written it for Otis Redding originally. So
and then
we did a little light research there at the end.
She made it famous. Yeah.
All right, so here's our warm-ups. Says, I'm sorry, I have to move my Zoom boxes. All right, says find the derivatives of the given values of the following functions. We have a table, and we have a p of x given as given in terms of f and g, and c of x given in terms of f of g. And you're being asked to find p prime of 5 and c prime of 5. Do I need to read the table, or?
No, I think we're good. It looks beautiful, and I know you worked hard on it because I watched you do it. So I'm going to tell a joke right now, and you should really pause this video and work on the warm-up, but you can hear the joke after you unpause the video. Here's a joke for you, Mark. It's not quite mathy, but it is sort of sciencey. So what does a cloud get for trying?
What does a cloud get for trying?
Precipitation points.
That's a serious stroke there.
That's a good 5th grade joke.
Yeah.
Nice and clean.
Yes.
Okay.
Light and fluffy. All right, Verge. So you want me to talk through this, or do you want to tell me what you got for p prime of 5?
Well, for p prime of 5, do you want me to steal the screen, or you want
that'd be awesome. Go ahead.
Okay, so you're going to have to keep those values there. I'm going to just go ahead and write down what p of x is, and then I'll write down. Let's see if I can share my screen. Okay.
Got it. Right.
So p of x is f of x times g of x. And so to find p prime, I would use product rule. So I do first f prime of x times the derivative of the second. Actually do it either way. I've been hanging around with Mark for too long because I just did it the way he does it. So first times the derivative of the second plus the second, g of x in this case, times the derivative of the first. And we're looking for p prime of 5. And so that would have been f of 5 times g prime of 5, and then plus g of 5 times f prime of 5. And then I had f of 5 was 2. Correct me if I'm wrong, Mark. G prime of 5 was 4 from the table.
Correct.
And then plus we have a negative a half and then times 3. So 8 plus negative 1.5 or positive 6.5.
Yeah, the negative half and the 3 are reversed, but of course multiplication is commutative. So
okay, so that was actually the value of f prime of 5.
yeah.
Okay. I'm going to go ahead while I have the screen here, because we're going to go back to the PowerPoint in just a minute. I'm going to go ahead and do the other function, and the other
Yes.
function was c of x, if I remember correctly. Was it g of f or f of g?
It is f of g of x.
Okay, so f of g of x. So c prime, I'm going to need to use chain rule. Now, this is actually the subject of today's lesson, but today's lesson is a review lesson. So I know everybody out there has already learned chain rule and has already practiced it and struggled with it and practiced it again and struggled with it again. Chain rule, and we'll take notes on this in a little bit. It's going to be f prime of g of x and then times g prime of x. So c prime of 5 ends up being f prime of g of 5 times g prime of 5.
Yep.
So g prime of 5 ended up being 4.
Correct.
G of 5 ended up being 3. I'm pulling those values from the table.
Yeah.
F prime of 5, or sorry, f prime of 3 was 9, and then
Correct.
9 times 4, 36. Final answer. So
Yay.
when I wrote in particular this one right here and how we originally presented it in the warm-up. So let's take a look at that warm-up again. Go ahead, Mark.
Yeah, so we both agree that it would have been a lot easier if the original problems had been written like that.
Yes, do that again. Go back to the way it was, just so they see that. And now, if the original problems were written with a little more clarity in the symbols, it might have been more obvious that we had a product for our P function and a composite for our C function.
And that's certainly something you can do for yourself when you're working it, like Verge did, right?
Yeah.
As you're reading it, write it a little clearer just to make sure the ambiguity isn't inherited.
That's true. Good point. So we're going to move on to our notes. And in these review lessons that we've been working on, what we've done is we've put in the shared folder, we've put the skeleton of the notes, so to speak. So I'm going to go ahead and steal this back again, Mark. Is that good?
Yep, that's good.
Okay. And I'm going to go ahead and work on the notes for the beginning part anyway. And then Mark is going to go ahead and work on a nice four corners activity with everyone. So these are the chain rule notes. And again, you probably have pages and pages of chain rule notes in your notebook from this year, but this is just a distillation of the high points for chain rule. So a couple things we could say here in terms of what we want to write down for chain rule is that what kind of functions are we going to use chain rule on?
Composite functions.
Yep, composite functions, exactly right. So that means that we have functions that are composed by putting one function inside the other. That's why we saw this idea of the f of g of x. And when we take the derivative with respect to x of f of g of x, we end up with the fact that we need to take the derivative of that outside function, f prime of g of x, with the inside function still in there, and then multiply by the derivative of the inside function, so times g prime of x. Anything else we need to put in this box, Mark, or you think that's good?
That's all right, unless you wanted to do did you want to do the derivative of y if
Yeah, sometimes you'll see
with
like
the u or something like that? Yeah.
so like if y is equal to u, then dy
some other
dx.
function of x. Yeah.
Yeah, some other more complicated function of x, not just x, and dy dx is equal to, and then what could we see these with the differentials all the time.
Yeah,
What could we write here?
So you do derivative of y with respect to u, since that's the way it's written.
This one here. Or
And then your chain rule, right, would be derivative of u with respect to x.
okay, so hold on a second. Get me from the beginning there, Mark.
Okay, sorry.
Uh-huh. So if you have y is equal to u, which is some function of x, go ahead.
So dy dx is on the left, right?
Yep.
On the left, right. Awesome. It's on the left, correct. And then we take the derivative of u with respect to x, right?
So then du dx.
Yep.
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 That's
and
good.
Then what?
No, I'm not sure I know what I'm doing here. I'm going to come back to that idea in a little bit.
That's all right.
Okay. All right. So let's go ahead and take a look at these right here. So these are, we saw some of these boxes yesterday where we had the derivative of x, for example, of sine x. Well, this is sine u, in other words, some sort of more complicated function, like it could even be another trig function that's put inside that sine function. So how would I take the derivative with respect to x of sine u? Well, that would be cosine of u, that inside function, and then times the derivative of the inside function with respect to x. So take the derivative of that outside function and then times the derivative of the inside function. Here, derivative with respect to x of cosine of u, this is going to be negative sine of u, but then times the derivative of that inside function, du dx. We put this one on the bottom of our sheet yesterday, derivative with respect to x of tangent of u. This one is going to be secant squared u and then times du dx. I kind of did the same thing yesterday where I went straight to those trig functions. I don't know why. I just like to do this.
You love your trig.
I do love the trig. I really miss teaching pre-cal and stuff like that, which I taught for years and years. All right, looking here at the derivative with respect to x of e to the u. So this would be e to the u, but then times the derivative of that exponent, du dx. Power rule, this is a times u to the n. So again, it's going to be n times a u to the n minus 1. Gosh, there's a lot of letters here, but then times du dx.
Yeah. Also emphasizes how u and n are just rotations.
Yeah, and you have to be very careful when you're making that u. Make sure it has a tail, because otherwise it's going to look like a v, and then v's and u's become very important in math as well. This one here we didn't do yesterday. This is an exponential function base a. The derivative with respect to x of some exponential function. Well, that kind of reminds me of e to the u. This is a to the u. So this is going to be, the derivative is a to the u, but then times the derivative of that exponent, du dx, and then times the natural log of a. Here we could say times the natural log of e, that's the base, but what's the natural log of e?
1.
1, so we don't really do that. This one's pretty obscure, but it's good to have written down anyway.
Yeah. If you forget it, you can use change of base, real easy to find it, but it is easier to memorize it is when it comes up.
So if you worked on your product and quotient rules circuit yesterday, probably bumped into these guys. The derivative with respect to x of secant of u. Okay, so the derivative of secant x would be secant x tangent x. So in this case, it's going to be secant u tangent u, and then times du dx. Make sure that you have that function that's inside in both of those places. Derivative with respect to x of cosecant u is going to be negative cosecant u cotangent u, and then du dx. And then the derivative with respect to x of cotangent u is going to be negative cosecant squared u times du.
Those cofunction derivatives are always negative. It's so bizarre.
Yep. So that's exactly what I was going to point out. Boy, Mark and I are like, this. It's amazing. It's so good. But yeah, the derivative of all those cofunctions are always negative. So
you can always tell if Verge didn't know I was going to interject something because that genuine laugh shows up. I am going to steal your screen just for a second.
Yep.
and go back and
I
talk
hope you're
about.
going to fix this.
Yes,
Are you
that's
going to
what it
fix
is.
this?
Yes, yes, it
Okay,
is.
yes.
Okay, so you can see mine now, right? All right,
Uh-huh.
and I'm even going to tie it to what you were doing because you were doing it perfect when it wasn't all abstract. So if we're taking the derivative with respect to x of some function y of u, and so like down here, e to the u is a function, and we can call it y, and it's a function e to the u. So we take the derivative of y to the u with respect to u. So the derivative of e to the u is eu, e to the u, sorry. And then because we took it with respect to u, but we mean to be taking it with respect to x, we do this chain rule of du dx. And then you can rewrite this because du's instantaneous change and du's instantaneous change are pretty much 1-to-1. And so you end up with the derivative of y of u over dx, or just dy dx, which this is just the derivative of that, which is dy dx. But
Yeah.
it's a way to play with the Leibniz notation and look at the, well, if as y changes to u times as u changes to x, then those changes of u are going to become independent of the relationship and go away.
Nice. Yeah, that's exactly what I was trying to do. Thank goodness you're here, Mark. I think there's a song for that.
It's not the one. It's not the one in my background.
Yeah, no, that's a good one too. This is what I was trying to write, and I've now written it properly.
Yes, all right.
Good, right? Okay. All right. So again, flying through calculus at light speed. A little bit about chain rule.
Hold on. Just, of course, we have this 30-second delay. If you guys didn't know, they're trying to keep us safe. Gonna steal it back. Where's
okay.
my? Apparently, I had this behind my face.
Oh.
so somebody texted me, slide it down. So yeah, so you can now the dy of u over with respect to du times du dx, and then the du's are going to go away. I talked through it, but apparently it was hiding behind me. So, all right, take her back. Sorry about that.
Okay. So back to this bottom part of our little review notes page, whatever you want to call it. One thing that's incredibly important, of course, if you're trying to take the derivative of composite functions, is that you then can figure out derivatives of they're not functions necessarily. They might be functions, but you can find the derivatives, you can find the dy dx of different relations by using implicit differentiation. So you can't learn implicit differentiation until you learn chain rule. This is a very traditional implicit differentiation problem right here. Very traditional. This one is very AP. So we'll go ahead and work through this one very quickly, but I do want to spend some good time talking about the other one. So it says here, find dy dx given x squared minus 3xy plus 4y to the fifth equals 100. So I'm not going to explicitly solve for y. I'm just going to go ahead and just start taking the derivative with respect to x and then solve for dy dx. So derivative of x squared with respect to x is 2x. Derivative of negative 3xy is going to be a product rule. I'm going to go ahead and keep the negative 3 out front. And then in the parentheses, really do the derivative of this product xy. So first, x times the derivative of the second with respect to x is going to be dy dx, plus the second y times the derivative of the first, or in other words, of this x, so 1. Close off your parentheses, and then plus derivative of 4y to the fifth is going to be 20y to the fourth, and then dy dx. And this all ends up equaling the derivative of 100, which is going to be 0. When you solve for dy dx here, if you've done these a lot, you can probably do all the algebra in your head. I'm going to go ahead and do a lot of it quickly right now, just to make sure, and Mark, watch me to make sure I don't make an egregious error here.
I already did it in my head, so you're checking me.
Okay.
Because I have mine written down, so we'll see if we end up at the same place.
Okay. Let's see.
Oh, and you rearranged the subtraction the same way I did.
Oh yeah, baby! Yeah,
definitely a mathematician's trick to saving seconds off your life.
Yes, exactly. Why put a plus sign if you don't have to? Exactly right. So that's our dy dx. That's a very traditional problem. AP tends to ask things that are a little bit less traditional, especially this year, given that students are going to have access to calculators and stuff like that. So here on this one, it says find the second derivative in terms of b, given that db dt, the first derivative, is equal to 6 times the square root of 10 minus b. So now I have to take the derivative of this expression here and with respect to t, and then I need to rewrite it so that my final answer is in terms of b. Okay, so I can do it. We're gonna be able to do this.
I trust you.
Okay, so I'm going to take the second derivative here with respect to t. So the derivative of 6 square root of 10 minus b is going to equal 6 divided by 2 square root of 10 minus b times the derivative of what's inside this 10 minus b. The derivative of that with respect to t is going to be negative db dt. Now I might do a little thought bubble on the side. Of course, I only have purple, but I might go ahead and do a little thought bubble on the side. I said this yesterday,
How
but
do you only have purple? You sent me 10 pens. How do you not have the multicolor pack?
I order purple for myself,
Okay.
just purple. And actually, just so you know, when I order it, I order the refills too. So
Yeah.
there's a pack that you can order that has like 3 pens and 10 refills or something. And so,
Nice.
yeah. So in my classroom, we memorize the fact that if y is equal to the square root of x, y prime is equal to 1 over 2 root x. And we know that. I said that yesterday. So that's where I'm leaping with this. I'm making a huge jump there. Some people might prefer to write this and use a power rule on it. In any case, I don't do it that way. All right, so let's see. 6 divided
Uh-oh.
by
Are we losing you, Verge?
not me.
Okay.
I can hear you. Can you hear me?
You're not moving anymore for me.
Uh-oh.
Oh, now you're moving. Hey.
Okay, sorry guys. All right, so what happened here was this negative dB dt is actually negative 6 square root of 10 minus b. So I substituted that in right here, negative 6 square root of 10 minus b. Ooh, this is so pretty. I can't take it. Look at these square roots are going to cancel out. And this, let's see, 6 times negative 6 is going to be negative 36, right? All divided by 2. So I believe I'm getting negative 18 here.
That's what I got.
Okay. That's a really nice one to rewind, watch me work it again, work it for yourself, maybe change the numbers on it tomorrow and work it for yourself again.
What's interesting is I did rewrite it as a power rule and I divided the 6 by 2 before I multiplied. So it's kind of a fun little, there's a lot of routes to get here. Before you take it out, I do want to, this because this is, to me, it falls into that same category of a line can be a solution, excuse me, a line can be a solution curve. Kids don't want to draw a line when they're asked to draw a curve. Number 2, the directions say leave in terms of b. There's no b in your answer.
True. But I
but
definitely want to.
But when it's constant, it's in terms of everything, right? It's in terms of j right now. When j is 7, the second derivative of b with respect to t is negative 18. It's in terms of everything, and I think that's kind of neat.
Well, that's unique to this function. That's the way it worked out in this function.
But if the variable goes away, you don't have to like try to slap it back in there somehow.
Absolutely. And here, what we don't want to do is leave it in terms of b and dB dt.
Right.
We need to move off of this. That's really what we could have left it right here, really, if we wanted to. Am I right, Mark?
Yes.
Yeah,
absolutely.
That would have been a happy answer. Happy, not happy, in terms of the way the prompt was written.
Yes. Yeah. So just want to get that out there because I know occasionally, that was a while ago that we did these. And so remind you.
Okay. Another thing about composite functions is that the definition of inverse is a composite function. If two functions h and g are inverses of each other, then h of g of x equals x, and similarly g of h of x equals x. But what happens when we take the derivative of this equation right here? So I'd need chain rule for that, and I get a result that helps me take the derivative of inverse functions, especially when I can't explicitly solve for y. So derivative of h of g of x equals x would be h prime of g of x times g prime of x is equal to the derivative of x is 1. So that means that g prime of x, the derivative of the inverse, is equal to the reciprocal 1 over h prime of g of x. In other words, 1 over the derivative of that evaluated at y, basically. Mark's probably going to drawing a picture right now. Am I right, Mark?
No, but I can because I love drawing pictures for
Yeah.
this.
Yeah, so I agree. I spend a lot of time developing this idea in my class, at least one class period on just this idea. So because this is a hard one to remember. And so if you can have an image in your head of what's going on, it helps to
I
make
just
sense.
stole the screen from
Yeah,
you.
it's great.
And I'm actually going to play with a real simple one. I'm going to start with the square root of x. And this is probably down by my face. Let me get that.
No, it's good now. Yep.
So goes through 1, 1, goes through 4, 2. That's just y equals square root of x. And then its inverse, which I guess will come in with a different color, also goes through 1, 1, because when you invert 1, 1, you get 1, 1. And when you invert 4, 2, you get 2, 4. And that's y equals x squared with the caveat that x has to be greater than or equal to 0, so that they're both inverse functions. And what we're going to do is, if we start talking about what Verge did over here with this h and j, is if I find the tangent line at 4, 2, so I can find the slope of that. And it's 1 over 2 square roots of x, so 1/4, right? Well, that's going to correlate to this point at 4, 2 in its tangent line. And the things I like to point out to my kids, because it's a natural, when you see reciprocals, you start thinking, ooh, they're perpendicular.
Yes.
But if this one's positive, this one's going to be positive. So no sign change. But this reciprocal, this multiplicative inverse, as I like to say, because I look for excuses to say multiplicative, is going to be 4. Because this is the derivative evaluated at 4. So that's here. If I want to put that over here. But then this is the derivative of the reciprocal evaluated at 2. Okay. And that's
derivative of the inverse.
Yeah. So all it's really doing is you invert the point, take the derivative of your inverse, and then the reciprocal of that evaluation. And I always do it as, where's it? The 3 things I always do is, where's it happen? What's the derivative there? And then flip it for the inverse. So just to give it, but it's that visual of when this one's shallow, this one's steep. If I stole a point down here that's real shallow, it's going to be super steep on my inverse. And so that's why this reciprocal is occurring. So I hope that helps. I don't know.
It totally does. And so I'm going to go ahead and really, I'm going to share my screen now.
Yep.
But I have already worked out this problem here. And you can take a screenshot of it and kind of follow my work. But pretty much I was able to explicitly solve for y.
You haven't taken it back yet, I don't think, have you?
Oh.
No, you have. Okay, sorry. My screens were arranged different. Sorry.
Okay, I was able to on this function explicitly solve for y. Then I took the derivative of that and evaluated at 5. So I mean, if you can explicitly solve for y, that's great. But the thing is that on the AP, a lot of times we're given information about a function, and we don't really know what the equation is or the graph or anything. We're just given a few little bits of information. So let's take a look here. The function f of x is an increasing function about which little else is known other than f of 2 is 7. So that means I have this point on f of x at 2, 7. And f prime of 2 is 5. So the slope here at x equals 2 is pretty steep. And we have some sort of a snaky thing going on here. There's my f of x. I don't know what it is, but there's my slope is 5 there. Then it says find the slope on the inverse graph of f and figure it out at 7. Well, 2, 7 on f of x is mirrored to be at 7, 2 on f prime of x.
Inverse.
Sorry, what did I say? I said f prime.
Yeah.
I meant f inverse. Yeah. So at f inverse on f inverse of x, there's this mirror going on here across the line y equals x. And I've got some sort of a snaky thing going here. But kind of like the picture that Mark just drew, this slope of the tangent line is still positive, though not as positive. It's got to be the reciprocal, and we proved it up here. It's got to be the reciprocal of that 5. So this answer would be 1/5.
Very nice.
Now, because I don't want to keep you guys here for 2.5 hours, I'm going to leave this as an exercise for you to do. You should be able to find this stuff pretty easy on Google or in your textbook or in your notes, and write down these rules here for yourself, because I do want to get into a few problems, or I want Mark to get into a few problems that are on the 4 corners. Oh, there's so many good problems on there. So go ahead and take a look at the 4 corners, Mark.
Right. And again, we borrowed this 4 corners from our friend Brian Passwater that's doing the BC ones early this morning. I think 9 Eastern, 8 our time. But he may not recognize it because we changed a couple of them to fit this lesson specifically. So do you want me to do this upper left one, Verge?
I think maybe do the numeric and the graph one first, and then maybe come back and
gauge
do the
time. This one is very accessible. It's a lot like the implicit that Verge did already. I'll just warn you in case we don't get to come back that this point x equals 4, you're going to need to find the y that goes with it. So you actually have to work with the original, and it may even occur at more than one point.
Hint, hint.
Yeah, might, wink, wink, nudge, nudge. So I actually had sorry, this is why we're not going to get to it. I had a girl this year make me a rectangular, she knitted it one night, a rectangular piece of fabric, and she knitted the word hint on it. So I could hold it up in class when I said things like that. Like,
hey,
there
Mark,
might be 2 points, and then I'd hold it up. And,
scoot your thing over so everybody can see the table.
So we can see the table.
Mm-hmm.
Thank you. I'm actually just going to go hide you over there, which means I'm going to look way to my right when and then you can see Freddie. Oh, geez, all kinds of stuff going on. All right. So we've got this table, and you can see the values -1, 0, 2, and 5 for x, and then the associated f and f primes. And g of x is f of f. Also, one of the wonderful times where we don't pronounce of with an f sound, or that would be really hard to say. So I can't find -1 immediately. I need to find the symbolic first, right? So we're going to come in and find g prime of x. We do f prime of f of x, kind of peeling away the layers of the onion. Do the outer one first. And then chain out your f prime of x. And then we're going to go find these values. So f prime of f of -1 times f prime of -1. Oh, and by the way, if you're wondering when the keys are available for these things, I know we've gotten some emails from teachers and students. Monday's key is already in the Dropbox. It's back in the Unit 1 folder. So if you're looking for those, this one will probably release Friday. So let's see, f of -1. Now I went outside in for my derivatives, but I go inside out when I'm evaluating. F of -1 is 0. So I'm looking at f prime of 0 times f prime of -1. My f prime at -1 is -3. And my f prime at 0 is 4. So G prime of -1 is -12.
That's what I got.
Yay.
Yay.
So pretty straightforward.
Reminds me a lot of the warm-up, but it is weird to have that F of F. So I think that's a
Yeah.
good one to do.
FFX. FFF. So weird that we pronounce it like it's spelled UV. I don't know. So h of x in this graphical one. So we've been given what? We've got this three, they're both linear piecewise functions. These three pieces right here are f of x. These three are g of x. You might want to color them if you're doing them on your own, because I got lost a couple doing it. I think Verge and I both got lost at different spots.
I was like looking at the wrong place when I was doing these.
Okay. And this is something that has happened before on AP exams, right? We talked about that yesterday a little bit, that they'll invert the G and the F from the rule you memorized. So make sure you understand conceptually what's happening, that is not F of G, it's G of F. So still going to do my outer derivative first, times my inner derivative. And let's see, I am going to bring some colors in. Let's see. So now we're going to find H. Oh, I didn't label it prime, did I? So H prime of 2. So if I want to go find, I guess, actually, sorry, talking to myself and you get to hear it.
Hey, wait a minute. We were going to talk about talking to
Yeah,
yourself.
I didn't have an inner dialogue right there. I'm having an outer dialogue.
Yeah, but you know, the cool
should
thing
have,
is,
right?
yeah, the cool thing is, like, all mathematicians talk to themselves all the time. And oftentimes it's silent because we don't want to bother everybody else. And definitely during a test, you can't be talking out loud while there's 30 other kids in the test room. But when you're taking your AP exam this year, you can talk to yourself out loud the whole time.
That's
the whole time. And so you can hear yourself make mistakes and you can correct them on the fly. And I think that's what Mark just did, right, Mark?
Yeah.
Yeah, it's awesome. Strategies for 2020.
That's right. Yeah, and you can talk to yourself out loud at this one, as long as you don't have a sibling in the room or something. Okay, so while Verge was discussing our inner dialogues, f of 2 is 3. I'm pulling that off the graph. I scoot up. Sorry. And I scooted my camera when I scooted my, oh no. Okay, I'm still moving. That's good. My camera just froze.
No, you're good.
Oh no, that was exactly what I thought happened last Friday. So, all right. So I'm gonna have to try and go back and forth. I'm sorry, this is tough. All right. So G prime at 3. Well, I have G, and at 3, I'm gonna scoot over to right here. I'm looking for the slope of the tangent. And your graph is much nicer. As I said yesterday, my computer's having trouble with graphics, but this is going up 2 over 3. So we have a slope of 2/3 on that linear segment. So that's my derivative. And then f prime at 2, well, we come back up here to f of 2. Now we're looking at this slope. And that actually is -1. And so h prime of 2 is -2/3. That's pretty neat. It's pretty easy, but you just got to keep track of, remember, your slopes are your instantaneous change or your derivative, right? And you be able to read values off the graph and not go to the wrong spot and jump around on the graph like I did earlier when I tried this earlier.
Yeah, me too. Mark, let's at least get started on the last one, because
the
that's
bottom
a
right.
really,
Okay.
yeah, that's a really great one.
So this one's cool. So this is our conceptual verbal. So you're told G is a linear function, and both G of 3 and G prime of 3 are equal to 4. So something's going on there. And then K of X is G of X over G of X plus 2. So then they took this line and shifted it to the left 2. And they want to know the derivative of this new function at 3. So I'm going to do the same thing I just did. I'm going to go find that conceptual derivative first, K prime of X. And this is just 1/2, right, Verge? I can just cancel those.
No, we're not friends anymore if you do that.
So putting kittens in danger, as it were.
You're not part of my friend group anymore if you do that.
I'm gonna put my camera in stationary and just put myself in the same angle as everyone else. Okay. Except you're picking up the camera. There you go. All right. So K prime of X, this is a quotient rule. It's
low to high.
So derivative of the low Oh no, derivative of that low d. Oh, see, and I don't even
You're
write
doing
it that
it
way.
right.
I do for derivative top times the bottom minus derivative of the bottom, g prime of x plus 2. And there is a chain here because our interior is a function of x. But it's not, there you go. It's not the function of, it's x plus 2. The derivative is 1. If you want to write it, awesome. If you don't want to write it, just as awesome. But it's good to have that internal dialogue where you ask yourself, what is the derivative of the inside? And then that's all over the denominator squared. So I'm going to go ahead and put the 3 in. I actually have done this problem twice now, and I did it different ways each time. So we're looking for g prime of 3 times, and 3 plus 2 is 5, so g of 5 minus g prime at 5 times g of 3 over g of 5 squared. And I know g prime of 3, I know g of 3. Those were 4. Okay. I don't know g of 5. I do know g prime of 5, but we have to think about that. It's a linear function. That's g prime of x. It's linear. It has the same slope everywhere. So the big thing is this 5. So I need to actually go find the function g of x. And I'm going to do that.
Oh, you're going to do your
using point slope.
Point slope,
so
the Mark
4
way.
plus 4. It's Taylor's way. But that's going to end up being 4x minus 8. I get a negative 12 there, and 4 minus 12 is negative 8. So, and you can see again there that g prime is 4. So now I can come in and I can actually do some arithmetic. G prime of 3, 4, g of 5. Well, I didn't actually do that, but
that's going to be 20 minus 8.
Yeah, 20 minus 8 minus 4 times 4 over g of 5 we decided was 12. And of course, as a numeric answer, I encourage you to leave it that way on an AP test, and I encourage you not to do it when you're, whoa! What did I do, Verge?
Well, you wrote you squared the 12 instead.
As I put it in.
Yeah, I saw you do it, but you caught yourself. You're good. Go ahead, put your paper up so people can see it a little better. Yep.
All right. So we've got 4 times 12 minus 4 times 4 over 12 squared. And again, I encourage you to leave it that way on an AP test, and I encourage you not to do it in a college course. You should go ahead and get a nice, pretty answer. 16 goes into 144 9 times. I know that because I've done a ridiculous number of conic sections. Because we love 9 squared and 4 squared on conic sections. And so that whole thing boils down to 2/9.
Yep. That's a great question. I love that question.
Maybe we should change Friday when we kind of do our wrap up for the week. Maybe we should throw another one like this at you, so you guys get to do one fresh without having seen it done. So.
Yeah, but like Mark said, you could do this one again and see if you get it right. I mean, what the heck do you think we're doing?
Right. As I'm asking the whole time, what am I doing? And,
yeah.
And when we talk about the AP exam, we're getting questions all the time from kids and teachers and students, like, what are they going to do about it? Well, you could Google it. You can't Google this. I mean, not super easily, not unless you find this exact problem. And so these kind of conceptual things are the types of things that I expect we'll see in May this year. So.
And plus, they're very they really don't need a calculator. I mean,
right.
You can manipulate and just leave your answer with that arithmetic there undone. That's totally fine. So what's in the shared folder today, Mark, besides our notes and besides the these 4 corners?
And you're living large right now.
No, you're living large.
Oh, it was me. Awesome. All right. So well, we've got the 4 corners. We've got the notes page. Is there a circuit today?
There's a chain rule circuit.
Chain rule circuit. Awesome.
We didn't do any of the examples off the chain rule circuit. So teachers who are watching or who might want to assign part of that to their students or all of it to their students, it'd be a great set of exercises. Yeah. I was going to say, go ahead, Mark.
Oh, I was going to say, and I said it earlier, but the Unit 1 key is up for those practice problems that we gave. There were some limit problems and 3 excerpts from FRQs at the end. So those are up as well, and they're in the Dropbox. If you go to this link here, use this QR code, go to the top level, go back to that April 13th Unit 1 review, and the key is in there now.
And we'll put the key from today, not for the circuit. We never put the keys for the circuit. I mean, all those answers are already there. You just need to work them. But we'll put those in the next couple of days. Tomorrow's Thursday, and we're going to be working on Unit 4, which has to do with, let's see, related rates, and all sorts of contextual applications of the derivative. So we definitely plan to see some more FRQ type style problems tomorrow, and for sure in our wrap up on Friday this week.
Yep, sounds good.
Mm-hmm.
So
Thanks
everyone.
Yeah, we really appreciate everybody joining us. We still have so many views. It's just fabulous. And I know a view counts only if you click in for a few seconds, but we hope you're even watching us still now. So
Bye.
bye.